Welcome back. In this video, we finish the chapter by seeing the proof for necessary and sufficient conditions for a graph to not be Eulerian but contain an Eulerian trail. And so what can we say? We say that G contains an Eulerian trail if and only if exactly two vertices of G have odd degree. We can say even a little bit more, that Eulerian trail must begin and end at one of these vertices. So it begins at one of the odd vertices and ends at the other odd vertex. So before I do this proof, this is actually quite a clever proof for this one. And it demonstrates a technique we might see later on it's quite useful in graph theory, and that is to modify the graph a little bit before proving anything with it. So we'll look at this example again. This was an example. This was G1 from before, that for second video I showed you. And we showed that this had an Eulerian trail but didn't have an Eulerian circuit. And that was because it had vertices of odd degree, which now we know a graph has to have every vertex of even degree in order to contain an Eulerian circuit. So what we're going to do here is we're going to turn it into a graph where every vertex has even degree. That'll give us an Eulerian circuit, and if we construct this new graph in a certain way, we'll be able to go from the Eulerian circuit to an Eulerian trail. So how do we do this? Well, take a graph with two odd degree vertices, let's call them U and V, and add a new vertex in, W, to get a new graph, say G1 prime, and we'll join W to U and to V. And when we do that, the degree of W will be 2, and since we added 1 to each of the degrees of U and V, now every vertex will have even degree. This gives us an Eulerian circuit. So let me, draw this Eulerian circuit. Here's an Eulerian circuit. And notice that UW, WV, right, those have to occur, those two edges, UW, WV, have to occur consecutively because W only has degree 2 in this Eulerian circuit. And so then we go from the circuit to an Eulerian trail and back to an Eulerian trail in G1 by removing W and those two edges. So let's formalize this. But this is essentially the idea. All right, so proof, we want to go two directions here. It's still an if and only if. So proof, all right, so if G contains an Eulerian trail, let's say a UV trail, Eulerian, I think that's a typo in the book, an Eulerian UV trail T, then we construct this new graph, H from G, by adding a new vertex W of degree 2 and joining it to U and V. Then T, together with the edges UW and WV, form an Eulerian circuit in H. And then we can say by Euler's theorem, or I guess we call that theorem 5.1, by theorem 5.1, every vertex of H is even. And so, since every vertex of H is even, remember H was obtained from G by adding this vertex W and joining it to U and V. So every vertex except for U and V in G must be even. And so every vertex except U and V are even in G. So that is U and V are the only odd degree vertices in G. And that's the forward direction. So if it has an Eulerian trail, it has two vertices of odd degree. Cool. Let's look at the backward direction. Again, we use the same construction. So let's let G be a connected graph containing exactly two vertices. Let's call them U and V of odd degree. And we'll show that G has a Eulerian UV trail. A UV or VU trail. So we do the same construction. So add a new vertex W of degree 2 to G and join it to U and V. Call this resulting graph, graph H. Then H, then every vertex of H has even degree. So by theorem 5.1, H contains an Eulerian circuit. But we can say more about this Eulerian circuit, where the edges UW and WV occur consecutively. And that was because W only had degree 2, and so it would have to occur consecutively. So deleting W from this circuit produces an Eulerian trail G that begins at U or V and terminates at the other. And that's the proof. So this is a nice technique. Hopefully we see this later on. Depends on what we can get to in the class. But hopefully we'll see this technique later on where we take a graph and we either copy it, something like that. We modify it by adding vertices and joining them to certain vertices of the graph. This produces a new graph that by some other theorem has a property, and that property is, then we remove the vertices, we sort of undo the process, but somehow some property is kept when we undo that process. In this case, that we would still have an Eulerian trail. So this is a nice, one of my favorite proof techniques is this. So that's the idea. So I think I'll end this video series here. This is the last video for chapter 5. I'll mention there are some other theorems in the text that get a little bit more specific. They can tell more. They give different necessary and sufficient conditions for a graph having an Eulerian trail. I'm not going to get into all that because I want to get to Hamiltonian graphs and I want to get to other topics in this course. So I'll sort of leave that to you. If you want, you can read those theorems. They're nice theorems, but I'm not gonna prove them in these videos. All right. See you next time.